Hello guys and welcome back. You have probably heard of hydrazine before. You know, the extremely toxic and reactive substance that is used as a rocket fuel. It turns out that it, along with its numerous organic derivatives, are incredibly useful and indispensable in many chemical reactions and processes. And one good example is also the star of today's video, where we will be synthesizing it. I am talking about this molecule, phenylhydrazine. If you dive a bit into hydrazine chemistry, one particular thing that seems to be true for most of its derivatives is their toxicity. Many hydrazine compounds are either quite acutely toxic or are even mutagenic and carcinogenic. That unsettling property is mostly due to the extraordinarily high reactivity of these compounds, and that is also why they are so useful in chemistry as well. You see, I have been working on a much bigger project recently, and for it I needed some phenylhydrazine. Of course, I didn't have it. So in this short video we will be making some for the upcoming grand project. So let's just start with the synthesis. To begin, I set up a round bottom flask and poured in 27 ml of distilled water. To this, I then added 48 milliliters of concentrated hydrochloric acid and enabled magnetic stirring. For the next step, we will need some aniline. This reagent is even more useful than phenylhydrazine, and it is also quite toxic. Interestingly, it also shares some use in rockets with hydrazine, as it was tested in some old hypergolic rocket engines. Anyway, I measured out 6.5 ml of cold aniline, and I added it to the acid. As you can see, immediately upon addition, a visible reaction takes place and some white smoke forms. This is just some aniline hydrochloride, and it is the product of this simple neutralization reaction. Besides, it also produces quite a bit of heat, and therefore I placed the flask in an ice bath. I will explain why this is important in just a bit. Now I need to add all of the aniline into the flask, and then we can proceed with the next step. I continued with dissolving 5.5 grams of sodium nitrite in 12 milliliters of water. That will create our deazotization solution. Next, I transferred all of the nitrite solution to an addition funnel that I attached to the flask. Now I am ready to start the next reaction. I very carefully open the stopcock on the funnel, and I adjust the drop rate to about a drop every 2 seconds, while maintaining the temperature between 0 and 5 degrees Celsius. This slow addition and the temperature control are extremely important here, and the yield drastically depends on them. We can also see that some reaction is taking place, judging from a brown gas that appears for a moment right after the addition of the nitrite, and the undissolved aniline salt quickly dissolves into the solution. You see, as soon as the nitrite solution drops into the flask, it reacts with excess hydrochloric acid to form this nitrous acid. This acid is just an intermediate, and it quickly reacts with the aniline hydrochloride to produce yet another intermediate, a diazonium salt. You can see that it is quite cursed, and that double nitrogen group makes it extremely reactive and quite unstable. It is especially sensitive to temperatures above freezing, so that is why ice bath is mandatory. Anyway, I now have to leave the reaction mixture stirring like this for roughly an hour to ensure that everything has reacted. After an hour on ice bath, it is ready. And you can see that it has changed color. This all indicates the progress of the reaction, and it is time for the last step of the synthesis. Since the diazonium intermediate is so reactive, all we need to do to it to convert it to the phenylhydrazine is to reduce it. There are many options, but one of the best is to use tin 2 chloride, so I opted for that. So I got myself a beaker containing 33 grams of tin chloride, and I added enough water to form roughly 75 milliliters of it. The cloudiness comes from the partial hydrolysis of the salt, which I tried to prevent by adding some hydrochloric acid to water, but oh well. So with the solution ready, I once again attached an addition funnel to the flask and poured all the reducing solution into it. Now everything I have to do is to once again very slowly add all of the tin solution to the flask while keeping everything ice cold. Like before, you can see that immediately a white precipitate forms, and that is actually our desired end product, phenylhydrazine hydrochloride. As more and more tin solution was added in, more and more precipitate formed, and eventually it got so thick that it was barely stirring. As more and more tin solution was added in, more and more precipitate formed, and eventually it got so thick that it was barely stirring. And once everything has been added, it had to yet again be left for half an hour to ensure complete reaction. With that out of the way, the last step was to just filter and collect it. I quickly set things up for a vacuum filtration and filtered the product. That is really it for the purification, as the product reacts with a lot of common lab solvents, and they are not suited for this situation. I really need the product to be somewhat pure, so this is okay. Anyway, that is pretty much it for this short video. As I said, I have a much bigger project going on and you do not want to miss it when it comes out. But until then, bye.